Hi everyone. So today we'll be talking about dental cements. This is one of the biggest chapters we have in dental materials. In this chapter, we discuss various forms of dental cements and all of their properties and everything. So since it's a very big chapter, I have summarized it in these two sheets. They contain everything you need to know. Okay, so everything you need to write in your answers, they contain all of that. And there are six major cements that we need to study. So zinc phosphate, zinc eugenol, glass ionomer cement, zinc polycarboxylate, zinc silicophosphate, and calcium hydroxide. So these are the six cements we need to know. Mainly, if a long answer is asked, then it's from these three cements, and these three are generally asked in short answers or could be asked in viva. Okay, we need to cover all of these six cements under the following headings. So, what you should know about all of them is first an introduction. Okay, I'll just highlight it over here. So, first an introduction. Then, second, you talk about the application. Third is classification. Fourth is mode of supply. Fifth is manipulation. Okay. Sixth is the setting reaction and what the cement looks like after setting. So setting structure, set structure. Okay. Then we talk about the composition and then we talk about the various properties. So adhesion, compressive strength, tensile strength, all of these properties we talk about. So I have made this table where we talk about all these properties. Okay. This is just a more organized form. It's easier to memorize and compare. So I think it will make the job easier for you. That's how I studied it in my second year as well. So starting with the zinc phosphate cement, this is one of the most commonly used cements in our clinics. Okay, also because this is cheaper. So this is why this is used a lot, and we'll discuss all the other properties as well. Okay, so starting with the zinc phosphate cement, it is oldest luting cement. Okay, so luting means adhesion. Adhesion is like sticking two things together, so it is the oldest luting cement. It is also called crown and bridge cement, and it is also called zinc oxyphosphate. Okay, so this is the introduction. It has various other commercial names as well, so Confit, Howard, and Motion Tennyson. These are the various commercial names that can be used as well. Then we talk about the applications. So where it is used, so it is used in the luting of restoration. As we said, it is a luting cement. It is used for high strength base. So base is something we apply when we make a cavity. So if this is your tooth and you made a cavity, you apply a base over here before filling in the amalgam or any other restoration to protect the pulp. Okay, so this can be used as a high strength base. Then for temporary restoration, so if you can't provide restoration immediately due to lack of time or any other purpose, so it can be used as a temporary restoration as well. It is used for luting of orthodontic bands. So the brackets you use, you can stick them onto your tooth using this zinc phosphate cement. Now the classification, so there are two types, type 1 and type 2. Type 1 is fine grained, so it is very fine in nature and it is used for luting. And the type 2, it is medium grained, so it will have slightly bigger grains and it is used for luting and filling. So it is used for restoring the tooth. Okay. Now coming to the mode of supply. So in what forms it is available in the market? So it is available in powder and liquid form and capsules. So if you know what it looks like, if you don't know what it looks like, so you will have one powder and one liquid, right? So either it will come in a separate bottle, powder separate and liquid separate, or it can come in a form of capsule which will contain half of the capsule will contain the liquid and half of the capsule will contain the powder. So you can just mix the capsule together and use it for restoration. Okay, then coming to the manipulation, so how you actually use it, right? So first 1.4 grams of powder is mixed in 0.5 ml of liquid. So this is approximately one big drop of liquid. Okay, and where it is mixed, so you take a glass slab. Okay, you take a glass slab, you put powder. So I'll just use yellow for the powder. You take 1.4 grams of powder, so you get like a scoop with the powder itself, and you take one scoop of that. Then you divide this. So you take the powder and then you divide this into about 4 to 5 increments. Okay, so you will take your stainless steel spatula and you will divide this I'll use a finer pen. So you'll divide this amount of powder into 4 to 5 increments, okay? And then you'll take one drop of liquid over here, and you'll take one increment from here, okay? You'll mix it into this powder in circular motion, okay? Then after this is completely mixed, and you cover a large surface area, right? Because the reaction is exothermic, so you cover a large surface area so that the heat will uh, it won't get built up over there, okay? Then you take the second increment and you again mix in circular motion. You keep doing that until you get the desired luting consistency or the base consistency. So remember, it is asked in Viva for luting consistency. What you will see, when you have your spatula, right? Let's say you have your mixture over here and you have your spatula. So when you lift your spatula from the mixture, you will see strings of about half to 1 inch forming, okay? So about half to 1 inch long strings of the cement will be formed. You will learn this in the practical manipulation as well, okay? And for base consistency, you should be able to make a tiny dough, okay? You should be able to make a dough of this entire mixture. So that is about the manipulation, okay? There are some other things you need to remember, that because the reaction is exothermic, you should be ideally using a cool glass slab, okay? You shouldn't have any water droplets on your glass slab, because that makes the setting faster, okay? So I have written down that you need to mix in increments. Okay, you need to mix in increments. The mixing time for each increment is about 15 to 20 seconds, and the total mixing time is 1 minute to 1 minute 15 seconds. Okay, the setting time is 5 to 9 minutes, and I told you the procedure already. Now coming to the setting reaction. So what happens? The liquid is phosphoric acid, okay, and the powder is a powder contains various other things. We'll discuss that in the composition, but it also contains zinc oxide. So you mix these together and you get an acid base kind of reaction, okay? So this forms zinc phosphate. Now the powder also contains aluminium the liquid also contains aluminium. So the aluminium from the liquid will come in and it will form something called zinc aluminophosphate gel, okay? And the heat. So what will the gel do? It will form this matrix, this shaded portion you can see. It will form the matrix of your entire set cement, and the unreacted zinc oxide, it will form the core of the cement. So this is what the set structure looks like, okay? So this is your um I'll use a different color. So zinc aluminophosphate gel is this matrix, and unreacted zinc oxide is this core. Now coming to the composition. So the powder, it contains zinc oxide 90%, okay? So this is the principal component. Then we have magnesium oxide as well, so it aids in sintering. It is a formation procedure, so it helps in that. Okay, then we have silica. It acts as a filler. So filler is like silica would be present over here somewhere, and silica would provide strength. Filler is something that provides strength, okay? And then we have barium oxide for smoothness. Okay, so these are the four components. It's not that difficult to remember. Zinc oxide you studied in the reaction, so it is, you know that it has zinc oxide. Something similar, magnesium oxide is also there, that aids in sintering. Then you have silica, so that is filler providing strength, and then you have barium oxide for smoothness, okay? Then the liquid, it contains phosphoric acid about 38-40%. So phosphoric acid is the main component. It reacts with zinc oxide. Then we have water, again about 40%. It controls the rate of reaction. Okay. Then we have aluminium zinc phosphate. It decreases the rate of reaction again, and it acts as a buffer. Then we have aluminium, so it came into the reaction we saw earlier. And then we have zinc, so this also acts as a buffer and helps in cohesion. Both of them, the zinc aluminium phosphate, you can see it delays the rate of reaction. How? Because it delays the formation of crystalline hydrates of zinc formation. So here whatever the reaction was taking place, it just delays the formation of that, okay? Now coming to the properties of zinc phosphate. So in the next page we have to talk about adhesion. So if the cement is sticking onto your tooth through chemical reaction? Does it bond chemically, or is it is just retaining there because of the shape of the cavity or any mechanical feature? Okay, so this is the two major type of retentions we have. So zinc phosphate, it has mechanical retention. Okay, it does not react with your tooth structure. So that is actually a disadvantage, because if your cavity does not have any retentive features, it will dislodge. Okay, it won't stay there. So the adhesion is mechanical. Then the compressive strength 103, it is weak. Okay, so it cannot be used as a permanent restoration. That's why it is used for base or luting. Okay, then tensile strength, again weak. Modulus of elasticity, it is suitable enough. Okay, so it is strong enough to bear masticatory forces. It is not it is good enough. Okay, then hardness. So hardness is similar to dentine, that is good. Solubility, it is fine, it is not that much, but if it stays in contact with the oral fluids for a very long time, then the solubility, then it leads to dissolution. Okay, then thermal insulation, it is good, and it provides very good thermal insulation actually. And the pH, so the pH, initial pH is very acidic, 3.5. It takes a few hours, so it takes quite some time to get to a neutral pH, which is a disadvantage. Well, it can be seen both as an advantage or disadvantage. The advantage is that it does reach the neutral pH, but it takes some hours, a few hours. Okay, so initial pH is acidic. Then it is non-radiant and radio opaque. So why is radio opaque important? So you can see it in the x-rays. Okay, so if you have a filling of zinc phosphate over here, because it is radio opaque, you would be able to see a very white thing filled in over here in x-rays. Or if accidentally it goes somewhere where it was not required. Okay, so if the cement is placed somewhere or it is swallowed, so you would be able to see it through the x-rays. Okay, then this is about modifications. Okay, modifications of the cements we need to talk about. So we'll be talking about three modifications: water settable, fluoride releasing, and germicidal. These are all modifications of zinc phosphate cement itself. Okay, so the water settable cement, then advantage is it is a single component, so you don't have a powder and a liquid both, you it is single component. Then how it is made? So the phosphoric acid is dried into the powder. Okay, it has inferior properties, so that's not really good, and it is suitable for luting or base, but it has other properties are inferior. Then we have fluoride releasing. So as the name suggests, it releases fluoride. Okay, so it contains stannous fluoride, and it is antibacterial and antikaryogen. So it is releasing fluoride, so it is antikaryogen. Okay, then we have germicidal. So it contains copper oxide and silver salts. Okay, that's why it is antibacterial. It is antiseptic as well, and it is useful in rampant caries. So caries which progress very fast, they are called rampant caries. So you can apply this cement over there, so the progress of caries will also reduce. Okay, now coming to the second cement, we are done with the first one. Coming to the second cement, that is the zinc eugenol cement. Okay, so zinc eugenol cement, it is again a low strength cement. Okay, it can't be used for permanent restorations and everything. It is a low strength cement. It is least irritating of all cements, and it is sedative, means it provides kind of a relief or numbness in that area. So it is more of a sedative cement than restoration or high strength. It is low strength cement that provides sedation in slight sedation in that area. Talking about the applications, so it is used for luting, lining, base. So we know luting, lining, base. Okay, root canal sealer. So this is used in endodontic procedure. Okay, you have to seal the root canal during various procedures. Periodontal dressing. So for healing of your periodontium or gingiva, it is used, and as temporary restoration. Now coming to the classification. So the classification, we have four types: type 1, type 2, type 3, and type 4. Type 1 is used for temporary restoration. Type 2 is used for permanent restoration. Type 3 is used for thermal insulation. And type 4 is used as cavity liner. So we talked about all the applications, and this classification is based on the application itself. Coming to the mode of supply, again we have powder and liquid form. So this is the most normal form we have. Then we have two paste systems. So one paste is the base. You get like two tubes like toothpaste. So one is the base and then other tube is the catalyst. Okay, base and catalyst. Now we'll come to the manipulation. Here the powder to liquid ratio is 4 to 1. Okay, so if you're taking um, 4 grams of powder, you would take 1 ml of liquid, or it can vary up to 6 to 1 as well. Okay, bulk of powder is incorporated or in increments. So I told you in zinc phosphate we took powder and we divided it into 6 increments, right? Here you can take the entire powder and mix it in the liquid, or you can choose to mix it in with increments. Okay, both is acceptable. You mix it with on glass slab and with stainless steel spatula. Okay, the setting time is 4 to 10 minutes. Complete setting may take 12 hours. Okay, so it can take long. Now coming to the reaction, so it is a hydration reaction first. The first reaction is a hydration reaction where you have zinc oxide. It reacts with water to form zinc hydroxide. Okay, then we have an acid-base reaction. The second reaction is an acid-base reaction where the zinc hydroxide will act as the base over here, and then we have hydrogen eugenol, this acid thing in here, which will act as the when the eugenol will act as the acid. Okay, and both of these will react. The zinc hydroxide and the eugenol will react, and it will form zinc eugenolate. Okay, so this will form chelate. Okay, and the chelate is, well, it is forming the matrix, but here we had the normal matrix. Here the chelate will join together and it will form an amorphous gel. Okay, the gel will later crystallize, so it will be stronger and it will impart strength to the set mass. So we formed various chelates and then they crystallize together, they join to form this matrix, right? The core, it is made up of unreacted zinc oxide like zinc phosphate again. So this is the unreacted zinc phosphate. And if I zoom in over here to explain to you once again, first we had zinc oxide, right? We have, sorry, we had zinc oxide, we reacted it with water, we formed zinc hydroxide. Then zinc hydroxide, which acts now as a base, reacted with eugenol to form zinc eugenolate. Now each of this crystal is zinc eugenolate. Okay, it is a chelate. These chelate, they bonded together and they crystallized to form this entire set matrix, and the unreacted ZNO, it formed the core. Okay, so this formed the entire set mass of this zinc eugenol cement. Now coming to the composition, so the powder contains zinc oxide. We talked about it in the reaction. It has white resin, so it decreases the brittleness because here crystallization is taking place and a set mass is being formed, so it could be brittle. So it decreases the brittleness. Then we have zinc stearate and zinc acetate. So they act as the accelerator or plasticizer. Plasticizer is something that holds everything together, and accelerator would increase the rate of reaction. Then we have magnesium oxide in traces. So it also reacts with zinc oxide in similar way to, but it reacts with the acid in similar way to zinc oxide. Okay. The liquid, it only contains eugenol and olive oil. So eugenol reacts with zinc oxide and olive oil is again a plasticizer which holds everything together. Coming to the properties, again the adhesion is mechanical like zinc phosphate. Okay. The compressive strength, it is weak again, and it is way weaker than the zinc phosphate. Tensile strength, again weak. Modulus of elasticity, it is lower, it is somewhat lower, and it can't bear as much masticatory force as zinc phosphate. Okay, hardness, it is low. Okay, so prone to wear off, it will wear off, it is not as hard as dentine, it has inferior properties. The solubility is very high, 0.4%, it is very high. So if it comes in contact with your oral fluids, it will disintegrate very fast. Okay, thermal insulation is good. Thermal insulation is good. pH initially it is 6.6 and it goes up to 8 immediately. So here is the major difference. If you talk about the highlight of this cement, it is that even initially it is not acidic. It is very slightly acidic initially, whereas zinc phosphate was very acidic initially. So this one won't be irritating at all, and it reaches a basic pH which is soothing and relaxing almost immediately. Okay, so that's why it is a very sedative and kind of relieving cement. It is the least irritant of all cements. So you can see the mechanical properties aren't very good, but in areas where we don't want strength, where we just want some healing and some protection for the pulp from thermal insulation, so we can use this cement. Now talking about the modifications, so the first modification would be non-eugenol cement. Okay, so eugenol is irritating to a few patients. So we made a non-eugenol modification of that. And what do we use in there? We used hexyl vanillate and orthoethoxybenzoic acid instead of eugenol. Then the second modification is EBA alumina reinforced cement. So this will provide better mechanical properties. Okay, so it contains alumina powder 30% and EBA liquid 63%. This will provide better properties and long working time. Then the third modification we have, it is the polymer reinforced or resin modified cement. Again, because we are incorporating resin and polymer, it provides good strength, better properties, and increased abrasion resistance. So you see over here the cement wasn't very tough. Okay, the hardness was low. Over here the hardness was low. So to provide better resistance, abrasion resistance, we made the polymer reinforced modification. Now coming to the third important cement, and actually the most important cement, the glass ionomer cement. So it is the most versatile cements of all. It is used almost everywhere. Okay, so the very the very highlight of this cement is that it has mechanical adhesion. So even in the introduction you will see adhesive tooth colored restorative compounds. So first it is adhesive, so it reacts with the tooth to provide the bonding. Then it is tooth colored, so you can use it in the anteriors and everywhere. And restorative compound, so it is used in the restoration as well. Now we have the classification and the application both summarized over here together. So the type 1 is the lutein type. We use it for adhesion, like we use zinc phosphate and zinc eugenol. Then type 2 is restorative. Type 3 is lining. Type 4 is fissure sealant. So fissure sealant is something, we have pits and fissures on our tooth, right? So if we want to provide preventive care to children mainly, we don't want food to get stuck in these fissures and pits. So we provide like a protective covering over here, very light covering to protect these pits and fissures, to protect them from food getting in there. Okay, so it is used as a fissure sealant. Then type 5 is an orthodontic luting, so we use it to stick our braces and everything on our teeth. Type 6 is core buildup. So core buildup is a technique that is used in endodontics. You basically, as the name says, you build up a tooth. Okay. Then type 7 is intermediate restoration. So that is for temporary restoration. Type 8 is atraumatic restorations. So in case of any fracture and everything, we use that. And type 9 is high strength base. Okay. So these are all the uses along with the classifications of this glass ionomer cement. There are 9 types and 9 uses. Okay. Coming to the mode of supply, so that is powder and liquid form and pre-proportion capsules similar to zinc phosphate. Again, it comes as a light cure system as well. So if you have studied composite resins, you would know this. If you haven't, light cure is something you just take the cement out of a tube of like an injection, right? You take it out one by bit, you place it in the cavity. If this is your cavity, so you would place a small amount over here, and then you will apply white light onto it, or any like the desired color light onto it, whichever one works for this type of cement. For resins it's generally blue. So you put the light on for some seconds and then it will solidify, it will harden. Okay, so that is the light cure system. Now coming to the manipulation. So the powder to liquid ratio is 3 to 1. So you would take 3 scoops of powder for 1 scoop of liquid, for 1 drop of liquid. Okay. Then how you mix it? So here you don't mix it on glass slab, okay, or you don't use a stainless steel spatula. You use an agate spatula, so that is a plastic spatula, okay, and on a mixing pad. So mixing pad could be anything like a paper. You get a mixing paper, or it could be a tiny piece of cardboard that is covered with slight plastic, okay. So you don't use glass spatula over here because this contains silica, it reacts with silica, so you don't use that. Powder added in increments, okay. So you would take the powder and you would again, you have this 3 scoops of powder, right, and then you would add it increment by increment into this liquid, and you will mix it in folding motion. So folding motion means you would mix it over here, you would pick the powder, you would pick the mixture from here and then place it in here, because the liquid is very sticky, so you need to kind of mix it in the way you form dough. You won't be exactly forming a dough, it will be slightly more stickier than that, but how you prepare a dough at home, in similar way you mix it, okay. So it is mixed by folding method. Mixing time is about 45 seconds. The setting time for type 1 is 4 to 5 minutes, and for type 2 it is 7 minutes. Then the reaction. So the acid attacks the glass surface, okay, silica. So in the composition we have silica and we have acid as well. We have various acids. So the acid will attack the silica. That's why we don't use it on a glass slab, because the glass slab also contains silica. So we don't want this acid attacking the silica on our glass slab, okay. Then the calcium, sodium and fluoride ions leach. Calcium polysalt gel is formed. Okay, calcium polysalt gel and silica gel both are formed. Okay, so they form the matrix. And how? So you have the core of again unreacted glass particles. So silica, that is the major component. Some of it remains unreacted and that forms the core. Then the matrix is formed by calcium polysalt gel, and this silica gel, it surrounds the core particles. Okay, so if I color code it, you would see the core. It is formed by unreacted silica particles. Then you have calcium polysalt forming the I'll just use a different color, calcium polysalt forming the matrix, and you have the silica gel surrounding the silica particles. Okay, then coming to the powder, the composition. So the first component is silica, about 40%. It provides hardness and translucency, so the tooth like appearance you get, it is due to silica. Then you have aluminium oxide, that is 30%. So it reacts with the polyacrylic acid and forms the matrix. So over here we saw the various ions leaching. Aluminium would be one of them as well. It would react and it would form the matrix. Then we have aluminium fluoride. So it provides the ions, right? Fluoride ion, calcium ion, sodium ions, they all provide the ions and they form the flux and they aid in centering. Okay. Then sodium fluoride improves working time, and aluminium phosphate controls the setting time. Then coming to the liquid, it contains polyacrylic acid in the form of copolymer of etionic acid, malic acid and tricarbolic acid. So we have 3 acids, etionic acid, malic acid and tricarbolic acid, which are all a form of polyacrylic acid. Then we have tartaric acid and we have some water. So this is the composition. It is a little complicated, hard to memorize, but you have to kind of go by the rote method. The setting reaction will help you to memorize this. So if I go over it once again, just to help you memorize the composition, because this one is slightly more complicated. First, you would know that we have silica, that is the major component. Then we talked about the ions leaching, calcium, sodium, phosphate, and aluminium ion leaching into here. So for aluminium, you can remember we have 3 forms of aluminium: aluminium oxide, aluminium fluoride and aluminium phosphate. Okay, then we have for fluorides, By fluorides, you can remember we have three forms of fluorides. Aluminum fluoride, I'll use this pen. We have aluminum fluoride, we have calcium fluoride, and we have sodium fluoride. So this will make it slightly easier to remember. Coming to the mechanical properties, so again, highlight of the cement that we have chemical bonding. Okay, the cement bonds chemically to the tooth. We don't need any retentive features. We don't need a box shaped cavity. If my cavity is like this, it won't get dislodged. It will stay there. Okay, so it is chemical bonding. Then the strength, the compressive strength, it is good. It is satisfactory for low stress restoration. Okay, it increases over time as well. The tensile strength also, it is low, but not ideal for high stress area. Okay, it can work for low stress areas but not ideal for high stress areas. Then we have this modulus of elasticity. So it can bear masticatory forces, it can bear the major masticatory forces. The hardness, it increases with time, it is satisfactory. Dissolution is very high. So whenever we make a GIC restoration, we apply Vaseline on top so it does not come in contact with your oral fluids, otherwise it will dissolve very fast. And the thermal insulation is good. It provides pulp protection, so it can be used for pulp capping, but we don't generally use it because it's expensive. The pH, again, the pH comes into play. The initial pH is very high, very low, sorry. So it is very acidic. It takes about 24 hours to get to a neutral pH, okay? And then coming about the distinct feature, chemical adhesion. So how does it bond chemically? It forms ionic bond between carboxyl group of the polyacid and calcium ions of the apatite of enamel or dentine. Okay, and then it releases fluoride, which helps in improves the anti-cariogenic properties. So what it means is, I have this tooth, right? This is my tooth, and I made a GIC restoration over here. So my tooth contains enamel, right? I have enamel in my tooth, and this GIC, it has some carboxyl group. So these two will bond, enamel 2 plus, they will form ionic bond, and it will provide adhesion between my tooth and the cement. Okay, again it releases fluoride. So we had three types of fluoride in the composition. Remember, we talked about it. We had aluminum fluoride, calcium fluoride, and sodium fluoride. So these all release fluoride, and fluoride helps in preventing caries, right? So it is also anti-cariogenic. It is also a distinct feature of this cement. Coming to the modification, so the first modification is resin modified GIC. So as the name suggests, it would contain GIC along with hydrophilic monomer, or HEMA. It is a type of resin basically. It increases the strength, aesthetics, and decreases the solubility of the cement. Then the second type of modification we have is the metal reinforced. So it contains some particles of metal. Why? What metals does it contain? It contains GIC along with silver amalgam powder. It is used for cold buildup and high strength restoration. Okay, so where we need strength, high load restoration, wherever we need strength, we added some silver amalgam in the GIC, and it increases the stress bearing properties of the GIC. The third type of modification, we have high viscosity GIC. So over here we increase the amount of powder we use, so that would increase the viscosity. It increases the properties, it increases the fluoride releasing ability of the GIC, and it is used for atraumatic restoration. Then we have nano ionomer cement. So we add nanoparticles into the GIC. It enhances the mechanical properties, aesthetics, and fluoride releasing ability. So that is anti-cariogenic. So it increases basically kind of all the properties. Then we have polyacid modified composite resin. So again, it contains some sort of resin, composite resin, and GIC. It increases the anti-cariogenic property, wear resistance, and better aesthetics. So since GIC is a very popular cement, many modifications keep coming in to enhance its aesthetics, strength, and everything, every property, right? So these are one of the major modifications. Since this lecture is getting very long and we have three more cements remaining, so I'll discuss the remaining cements in the next lecture. I hope this lecture will help you and the notes will help you. For the notes, you can go on to the Telegram channel. Thank you.